Alright, so we're going to take a look at some orbits here. So I have the Universe Sandbox set up. I'm going to zoom in on Earth. This is just a simulation of the solar system. And we're going to start putting some things in orbits around Earth. So I need to slow down this simulation a bit so we can actually see the orbits a little better. Alright, so I'm going to add a couple satellites into orbit. I'll add James Webb in low Earth orbit for some reason. I know it's not in low Earth orbit, but just for the sake of the simulation, we'll put it in a nice, close low Earth orbit. You can see it's moving really fast. So low Earth orbits, they move really fast. That's tends to be around 90 minutes or so for it to actually do a full rotation around Earth. They can be in all sorts of directions. They can be along the equator, they can have some inclination, they can be in polar orbits. So let me do my best to move one of these guys into a polar orbit. Let me change the inclination. A polar orbit is in, or has an inclination of about 90 degrees. Like that, so you can see it's now moving in a polar orbit. Low Earth orbits are advantageous because they're a lot closer to Earth. So for imagery, if you're in low Earth orbit, you can get higher resolution images without needing a better camera. Just because the objects it's taking pictures of, whether it be a storm or a building or whatever it is, it's a lot closer to that source that's trying to take the picture. It's also good for comms. So if you actually want to have communications, like telephone or internet through low Earth orbit, you do need a lot of satellites because they move so fast. But the latency is pretty low for low Earth orbit satellites because it doesn't have very far to travel. The signal doesn't need to travel very far. Now let's move on to middle Earth orbits. So I'm actually going to delete these because it gets pretty congested in the simulation with all these lines from the individual satellites. So we'll now add something in middle Earth orbit. We'll do the Hubble Space Telescope. So I actually don't have the range of altitudes for middle Earth orbit memorized, but we'll say it's somewhere around 20,000 kilometers or so. And this simulation defines the altitude actually from the center of the Earth rather than the surface. So that's roughly middle Earth orbit there. Middle Earth orbit is kind of the in-between because it's not quite as nice with staying in the same location as Geo, but it's not as close as Leo. So one of the most common things in middle Earth orbit is GPS. GPS satellites all orbits in a MEO orbit. And if I didn't mention before, LEO is another term for low Earth orbit. It's the abbreviation. So as I speed this up, you can see this satellite in MEO is rotating around, but it's moving a lot faster. It's still moving faster than Earth is rotating. So it's not always going to be over the same location. Alright, that's kind of all there is for MEO. So let's go to GEO. So GEO orbit is roughly at about 36,000 kilometers up. So I'll do the Cassini space probe this time. And since this measures from Earth's center, I'm going to have to add about 6,000 to the altitude here. So let's see, 36 plus 6 is about, I'll say it's about there. So it's not going to be perfect, but you can see that the GEO orbit does, in theory, match the rotation of Earth. So that as it's moving around, Earth is spinning at the same frequency. Let's speed it up. Yeah. So it's geostationary because I did put this at the equator. So you can see it's at Earth's equator, if you can recognize the continents there. But it can be at the same altitude in a geosynchronous orbit. So geostationary means somebody on Earth is always going to see it in the same location of the sky. Geosynchronous is an orbit at the same altitude from Earth, but the inclination is not equal to 0. In other words, it's not orbiting directly at the equator. So inclination, we're going to change this to 9 degrees. So we'll just do like 20 degrees just for the sake of demonstration here. Somehow that changed drastically its altitude. Let me see if I can change that back. So distance, we'll change this back to about 42,000 kilometers. See if that fixes it. And it crashed into Earth. Okay, let's try this again. We're gonna add another object at a geo orbit. So there we go, it's in geo. We're going to select it again, change the inclination. I'm just going to type it in this time rather than play with the slider. That seems to mess things up. So we'll do the inclination as 20 degrees. And now you can see it's still orbiting with the same rotational speed or rotational velocity as Earth's surface as it's spinning. But it's moving up and down. So on the left-hand side here, it's kind of up in the orbit. On the right-hand side, it's down. And what this would look like from the surface of the Earth is somebody watching the satellite generally in the same part of the sky, but it would be moving back and forth or up and down depending on which direction they're looking from or which perspective they have looking at the satellite. It's not going to be stationary, but you can still always see the same satellite in the sky. And this is really useful for satellite dishes, collecting or sending information, because they don't need to track an object really far across the sky. They don't need to flip to another object to continue a transmission. It offers a kind of an easy single point that you can always aim for, but geostationary is really the ideal type of satellite because you don't have to move the satellite dish at all. Once you get it pointed in the right direction, you just kind of set it and forget it there. So that is geosynchronous. So now let me show you highly elliptical. Let me slow down the simulation. Oh, and one other thing about geostationary and geosynchronous is they have a hard time seeing the poles. That's because as they orbit, it's still always centered around the equator. Even if it's not orbiting at the equator, it still crosses the equator each time. You can't really have a geosynchronous orbit with a 90-degree inclination going over the poles, because then it's not really quite as useful at that point. Because when it's at 90 degrees, is it really following the surface of the Earth at that point? Not really. Let me focus back on Earth and click delete. Alright, so highly elliptical orbits. They solved that problem of looking at the poles by providing or mimicking a similar property of geostationary orbits. So you can get a long look time down at the poles. So let me put another object in orbit. And we're going to change the eccentricity this time. So the eccentricity right now is at 0, so let's give it a value of 0.5. There we go. So this isn't really centered at the pole right now. I'm just kind of centering it down at the equator just to give you an idea of what it's doing, but I'm afraid to make it crash into the Earth again. So here you can see when it's close to Earth, it moves really fast. When it's far away, it moves a lot slower. So here, long look time, very short look time, long look time down, short, long, and it just continues like that. So it's good for both comms and imagery because you can get a lot of images over the same location for a while. I should probably give this an inclination of 90 just to show this a little better. There we go. Okay, so now you can get a long look time at the South Pole in this case, and short look time over the North Pole, long look time. And for comms, you also have a satellite that tends to be or spend a while in the sky here. It's not perfect for comms. You might need 2 or 3 of these to always have a satellite that you're connecting to. But the point is, when it's far away, it goes a lot slower. It spends a lot more time over whatever location you want. It doesn't have to be the poles either, but it's most often used for looking down at the poles. So that is highly elliptical, or HEO. A lot of people call HEO high Earth orbit, but that's not really a commonly used term, at least that I've ran into. So let me delete that. And the last one I want to show is choose an object, is a sun-synchronous orbit. So this is why it shows a simulation of the solar system as well, to include the sun. So I'm going to try to put this best I can on a sun-synchronous orbit. It's not going to be able to process with the Earth, but it will hopefully get the point across. So right now we have an orbit going around Earth. And I intentionally tried to make this perpendicular to the motion of Earth around the sun as well, just to get the point across that a sun-synchronous orbit generally faces the sun, or faces a direction that precesses around Earth as it's orbiting. So right now I'm zoomed out. That line of the orbit, if you can see on my mouse, is kind of facing the same direction as the Earth to the sun. But as Earth moves around the sun, that direction wouldn't be pointing at the sun anymore. So sun synchronous always points at the sun. And it does that actually by taking advantage of Earth not being a perfect sphere, which means the force of gravity is different depending on where it is in the orbit. I mean, it can take advantage of that to cause the orbit itself to precess about 1 degree per day. So in this case right now, it would maintain this direction with the sun. So as it's on the right side, it's pointing more horizontal or left to right as it orbits around. Again, as I move my mouse, kind of imitating the orbit. As it gets to the top, then it's moving more up and down, and it just kind of keeps precessing around Earth as Earth orbits around the sun. And the big advantage of this is shadows. If you set up a sun-synchronous orbit where it goes over the same location on Earth, maybe once every 10 days or so, you can get a full, or mostly full, view of Earth with the shadows all in the same location. So if you're looking for changes on Earth, you won't have to worry about accounting for shadows at different times of days that you are taking images. That's really all there is for the basic types of orbits. And if all else fails, you can always just drop a sun in the middle of the solar system and start over. I was hoping that would go supernova. Let me choose. There we go. I added enough stars. So yeah, all else fails, just do a supernova.